In this video, I'm going to speak about steady state error. So in the previous video, I talked about the feedback control system, which talks about for a given system, which represented by G sub s. So G sub s is the transfer function for the system, which is typically given by the ordinary differential equation, and the control is generated by comparing the difference between the input and output, and we apply certain control a method for example the PID control, and we generate the control input that will be applied to the system again, and the output will be y sub s or y sub t in the time domain, or y sub s in the s domain. So y sub t of t and y sub z can be converted from one way to another by using the Laplace transform or the inverse Laplace transform. So the difference, by calculating the difference between the input, which is r sub t or capital R sub s, and the output, which is either y sub t or y sub t, typically is given by r sub t minus r sub t minus y sub t, we can try to figure the difference. And the difference plays an important role because our goal is to drive the difference between the y sub t and the I sub t to be 0 as t goes to infinity. Okay, this is a general the feedback control system. So the steady state error means the value of y sub t minus r sub t as t goes to infinity, which means as time goes on, for example, I give certain r sub t and we calculate y sub t by given a control system, given a control and given system, and given the sensor like feedback h of s. So what is the final error between the y sub t and r sub t? So apparently this can be considered as one metric to quantify the control performance, which means if we apply our algorithm, like the control algorithm, eventually what's the difference between the output and input? So that's one metric to quantify the control performance. So later on we'll talk about some other metrics to quantify the control performance as well. So through this lecture, I'll talk about how to compute the steady state error, which means what is the value of y sub t minus r sub t as t goes to infinity. Okay? So there are mainly two approaches we can use to compute the steady state error. So apparently this y sub t typically is given, the input is already given, so we just need to compute the y sub t and then compute the limit. So direct approach talks about the way we need to compute the y sub t. So now the first one is we have to compute y sub s given this block diagram. So we are talking about how to compute for the block diagram, how we compute the relationship between the input and the output, which is called transfer function. So we can compute the y sub s given r sub s is given by this form. So for if you still remember for the block diagram, so I have a cascade, which is a GCS and GSS a cascade. So that's a product of these two if you put them together, and then we have a loop, okay. So if you apply cascade and the loop, now you will end up getting this. We're gonna end up getting this transfer function. Use the property of the block diagrams. So we do the cascade. So this one include right over here, cascade first plus feedback. So we'll get a transfer function. So this part will be just transfer function. So once we know transfer functions, the output will be just the transfer function times the input. Okay. Once we have y sub s, now we can compute the limit of t go to infinity, y sub t goes to r sub t, which is limit as t go to infinity. I take an inverse Laplace transform of ys minus r sub s. Okay, this is called inverse. Then we can, if we can compute the limit will be the steady state error. So again, typically this r sub s is given, so we just need to compute it. This one is also given by the limit t goes to infinity, L inverse y of s minus L inverse r of s. Okay, this one is also r sub t. Okay, now this is true if and only if you can separate them if this limit exists. Okay, if they don't exist, you probably cannot separate them. You still have to compute this, and you try to find the limit. Okay. So that's about the first approach. The second approach is indirect approach, which means we may not want to compute y sub t directly using inverse Laplace transform. There's probably an easy way, like I mentioned, the final value theorem we can apply. So this is called indirect method. Okay, so for the indirect method, we do the same thing. Okay, we compute ys minus r sub s. We do the same way, and ys again given by what do we compute over here. So once we have that, we can merge them together. So we can end up having this, which just put this one together. You sort of have this guy minus 1. Okay, so it's the denominator and the numerator minus the denominator as a new numerator and divide by the denominator here. Okay, so this is ys minus r sub s. So the indirect method says the limit of y sub t minus r sub t as t go to infinity is equal to the limit of s go to 0 as, don't forget about this s, time ys minus r sub s. So this is final value theorem. Okay, so the condition is the I should write it here, ys minus r sub s has at most one pole as the origin, and all other poles are in the open left half plane. So that's the condition we can apply the final value theorem. So that is needed if you use the final value theorem. Okay, if this holds, we can just use, we don't need to do the inverse, we can just compute the limit of s go to 0 as, again, don't forget about this, s time ys minus r sub s. Now we're done. Okay, so here let's see, I want to give an example showing what's going to happen. Okay, for example, what if I have r sub t, which is 1, r sub t each 1, which means your reference. So this is what I want to show you right here. So this is, if this is t, so r sub t is 1 means if it's less than 1 is 0, it's greater than equal to 0, so this is 1. So this is r sub t, so this is 1, this value is 1. So you almost have a step function over here. So when you do the Laplace transform of this r sub t, so this one you use Laplace transform, you get a r sub s, this is in the s domain is 1 over s. You can use table to find out. Once we have that, so I can have ys minus r sub s is all the stuff over here. Okay, so what I do is I just replace this guy by 1 over s. Okay, so it's divided by s right over here. So it's GCS GS minus 1 minus GCS GS HS divided by s time 1 plus GCS GS HS. The difference is I just replace, like I mentioned, replace the HS by 1 over s. We're done. So if the poles of ys minus rs, so it's given by, so the poles of this guy is you set the denominator to be 0. You set this guy to be 0. Okay, so you find the solution. So apparently one of them is s equal to 0. The other one is 1 plus GCS times GS times HS equal to 0. So that's the whatever solution that's for this equation will be the poles for ys minus r sub s. So here we assume that the solution to this guy is, are all in the open left half plane, so which satisfies the condition because I have one pole at the origin and others in the open left half plane. Okay, so if that's hold true, we can compute the limit of t go to infinity yt minus r sub t. Now here we can use the final value theorem since the condition is satisfied, which is limit s go to 0 s ys minus r sub s. So now we replace this guy by what do we compute over here? So limit s go to 0 s, again don't forget about this s time, this will repeat the whole thing again over here. Now fortunately we get s cancelled out over here. So as s go to 0, the limit we just replace everything. GCS replace s by 0, all s by 0 we get it over here. So this is steady state arrow. Okay, that we can compute up here, assuming that is the solution to the equation 1 plus GCS GCS. Okay, this here one should be GCS GS HS solution in the open left half plane. So this will be the final, the steady state error. Okay, now I'm going to give you a specific example talking about, for a feedback control system, the control parameters, not only the control form, but also control parameters have an impact on the steady state error. Okay, that's why even for the control, not only the structure of the control, but also the control algorithm, but also the parameter in our control matter when we talk about the feedback control system. Okay. All right. So the example I give you here is pretty simple. So this is the system give you. So this is the system. It's very simple. So this is just a single integration. So this one in the time domain is just integration. Okay, it's just integration of that, which means if this is my u sub t and this is a y sub t, so you basically u sub t, you do the integration will be the y sub t. So that because the 1 over s is integration. Okay, so we have just the unit feedback. So the feedback here is just 1, so make it simple. And also my control is k1s plus k2, which is called PD control. So this is my proportional control. This is my derivative control. Okay, if you don't know this, so check my previous video. I talk about what is the PID control. Okay, you can talk about why that's the PID, if that's PD control. Okay, so assuming that's what we have, and also for the input r sub s, I assume that is 1 over s. In other words, if I use r sub t as my in the time domain, so this is given by 1. Okay, so the input is also a step input. I want to figure out, hey, what is my output y sub t and what's the steady state error? So my goal is to compute the steady state error, which is the limit of yt minus r sub t as t goes to infinity. Okay, so it doesn't matter which method we're using, direct method or indirect method. The first step is we also have to compute what is my y sub s. Okay, so before computing y sub s, when you compute the transfer function, okay, again the transfer function is we can use the property of the block diagram, because this is we have one block over here, and there's a feedback loop. Okay, so by using the property of the cascade and feedback, we can compute a transfer function of this system, the closed loop, the feedback control system. Is because the cascade is just this guy times this guy. Okay, this guy times this guy. And that feedback loop is 1 plus this guy times 1. Okay, times 1 doesn't matter, so it's 1 plus the whole thing over here. Okay, so if you multiply both the numerator and denominator by s, so we can simplify this one a little bit by k1s plus k2 plus divided by s plus k1s plus k2. If you put a little bit simplify into a simplified version, is k1s plus k2 divided by 1 plus k1s plus k2. So that's the transfer function. So apparently my y sub s is the transfer function times the input r sub s, which is k1s plus k2 divided by 1 plus k1s plus k2 times 1 over s. Remember my input is 1 over s, r sub is 1 over s. So this one, the difference I just do here, k1s plus k2 divided by 1 plus k1s squared. If you do this, the product, so get s squared plus k2s. So that's it. Now we're going to compute ys minus r sub s. Okay, if we do this one a little bit of computation, we get ys minus r sub s is this guy, repeat over here, minus 1 over s, this is my r sub s. Okay, so we make the denominator to be the same, so we can do the subtraction. So we'll keep this one to be the same, and for this guy, we multiply both the numerator and denominator by 1 plus k1s plus k2 to make the denominator for the first one and second item to be the same. And apparently the first denominator and the numerator will be different. It will be 1 plus k1s plus k2. We just repeat that. If we do the subtraction, we get minus over 1 plus k1s squared plus k2s. So nicely, so this s can cancel out over here. So we get a negative 1 divided by 1 plus k1s plus k2. So that's the ys minus r sub s. Okay. Now I want to think about, okay, what is the limit of of minus r sub t s equal to infinity. So apparently k1 and k2 may affect the final value, because if you choose differently, maybe you get a different value, right? So the question we have, first question is, do we get the same steady state error for different k1 and k2? So as you can see, it may not be the case. For example, if I let k1 to be -1, so this will cancel out. So for different k2, you get a different steady state error, basically, right? So definitely they should be different, right? The second question is, what are the steady state error for different k1, different possible k1 and k2? So next I'll talk about 4 different cases. I'll go over a few different cases that cover all possible choices of k1 and k2, and also I'm going to show you what's the final steady state error. Okay. So the first case is that we'll consider the value of this guy and this guy. Apparently this is the property of negative value or zero value will matter. Okay. So we'll first start with what do we have? 1 plus k1 is positive and also k2 is positive. That's probably a simple way we can start with. In other words, we have k1 is greater than -1 and k2 is positive. So by computing the poles of the y's, because the poles really matter. So the poles of y minus fs, you just set the denominator to be 0, is 1 plus k1s plus k2 equal to 0. So the pole will be equal to -k2 divided by 1 plus k1. You just move the k2 to the right hand side, you get a -k2, and then divide by 1 plus k1. So because k2 is positive, 1 plus k1 is positive, so because if you have negative over here, so again this is negative. So poles actually this is the open left half plane. Okay, we have one pole and the pole is in the open left half plane, so we can use the final value theorem. So the limit of this guy is equal to, by using final value theorem, okay, do it here, with the limit as s equals to 0, s, don't forget about this s over here, s times ys minus r sub s. Okay, if you do the limit, s times this whole value over here, so this will be 0. As s equals 0, this will be, because this guy be 0, this guy will be some value. Okay, so the product will be 0. In other words, if this guy and this guy is positive, so my steady state error will be 0. Okay, case 1. Case 2 says, what if I have 1 plus k1 is positive while k2 is negative? Okay, which means I have k1 is greater than or equal to -1 and k2 is less than 0. So again, we can compute the poles of ys minus r sub s. You follow the same approach. The poles will be again negative k2 plus divided by 1 plus k1. So the difference here is because k2 is negative, so that the poles are the pole is positive. In this case, the final value theorem does not apply anymore. Well, fortunately, it's easy to compute the inverse. Compute is limited directly because I can compute the inverse Laplace transform. Okay, so in this case, I can do a little bit of math, so which is given here. So do ys minus r sub s is -1. This I repeat again. Here what I do is I divide both numerator and denominator by 1 plus k1. Okay, so -1 divided by 1 plus k1, and denominator do that one s plus k2 divided by 1 plus k1. Okay, so now I can compute the inverse Laplace transform to get the y sub t minus r sub t. Okay, if I apply the inverse Laplace transform for ys minus r sub s, which is given by this over here, which is given by this. Now I can pull, this is constant outside, so this become 1. Okay, leave it over here. So if we use a -1 divided by 1 plus k1 again, so this inverse here is just e minus k2 divided by 1 plus k1 times t. Okay, this is how to figure out it. You can use a table. Okay, use a table to check what is this inverse of this guy. Okay, this is like basically 1 plus s times a. So let's do inverse. This is e minus at. That's it. So you apply, change a by this value, you will get this inverse Laplace transform. Now here, if you look at this value here, so k2 is negative, and 1 plus k1 is positive, and then we have negative over here. This become positive. Once this is positive, and also this guy is -1, so this guy is positive, and also this 1 plus k1 is positive. So this is the whole part here. It's right here. This is negative. Okay, so the limiter, so because this is negative, this is e to the positive time t, and if t goes to infinity, this is just go to a negative infinity. So the limit of this guy will go to negative infinity, which means you can also say this no steady state error. You can also say there's no steady state because your state will keep growing, which means you somehow like this. Okay, if I draw somehow like this, let me draw it over here. If this is my reference, so the reference is always 1. Okay, let's draw it over here. So reference is somehow over here is a step function which is 1. And my y sub t is somehow, I don't know what is the first value, just do some, just some guess. It's something like this. Keep going, keep going, keep going. It's positional decay. So which means you don't have steady state error. Your error will keep growing, okay? So let's try to find here this purple line, which is r sub t, and the red line here is y sub t, sort of. Okay, and of course this is my time sub t over here. So this is case 2. So case 3 is opposite, is 1 plus k1 is negative and k2 is positive. Okay, so this one you can follow case 2, and you can find a limit of t go to infinity, yt minus rt will go to positive infinity, which means this yt go up. Okay, so again, this is follow. You can, if you follow case 2, you can compute the limit, and it will go to positive infinity. For case 4, if I do 1 plus k1 is less than 0, k2 is less than 0, you can also compute the limit of t go to infinity, yt go to 0. You follow case 1, so which means your pole is open left half line. You only have one pole. The pole has its own in the open left half line. So again, this limit will go to 0. Now we can do the case number 5. Is what if the 1 plus k1 is equal to 0? Okay, which means k1 is, if I look at this one, so this is my ys. Let's go back over here. So my ys minus r sub is over here is negative 1. Okay, let's write over here. So my y of s minus r of s is negative 1 over 1 plus k1 s plus k2. So if that for case 5, you basically have here is 0. Okay, this is here is not 0. Apparently, I cannot have both to be 0. If it's supposed to be 0, you're going to go to infinity for sure, right? If this guy go to 0, but this k2 is not equal to 0. In other words, I have k1 is negative 1, k2 is not equal to 0 here. So ys minus s here become negative 1 divided by k2. And if I do the inverse Laplace transform, this guy gives me L inverse ys minus s. This gives me negative. If you use a table, okay, use a table, the inverse, you get negative 1 divided by k2 times this is delta function. Delta function will drive it go to infinity. Okay, so which means either you go to negative infinity, positive infinity. So you won't have a limit as well. The steady state, no steady state error as well. Okay, for the case number 5. For case number 6, do the opposite. If I have 1 plus k1 is non-zero, while k2 is 0. So in this case, so ys minus s is negative 1 divided by 1 plus k1 times s, because here this guy equal to 0. Now if I compute the pole, you set this guy to be 0. Okay, which means I have s is 0. S being 0 is the only pole. So this is at the origin basically. So you have at one pole at the origin, which is fine. Set it at the final value 0. So I still can apply the final value 0 to compute the limit of yt minus r sub t as t go to infinity, which is limit as t go to s go to 0. S don't forget about this s time ys minus r sub t, which is negative 1 divided by 1 plus k1 times s. So this s will be cancelled out. So I have negative 1 divided by 1 plus k1. So it doesn't matter what s value we select. So basically I have equal to negative 1 divided by 1 plus k1. So this is a constant final we say non-zero steady state error. So from all these cases, what we can see here is we could have 0 steady state error. We could see the state goes infinity, which means there's no steady state error. The error go to infinity. We also could see the error could be a constant value. It's non-zero. Also, it's non-zero constant value. Which means if I go back to this original problem over here, so for a given simple like a control system, like a given system like this, even if I apply the simple control like a PD control, the parameters do matter. So if I select different parameter, I could have zero steady state error. I could have a constant steady state error. I can have no steady state error, which means the state go to infinity. Apparently, those state go to infinity is not desired. But for those one with zero steady state error, we could also select different K1 and K2. Remember over here, for example, here I have K1 and K2. So if I look at this, the steady state for the case 1 will go to 0. So you have numerous options of K1 and K2. You can say K1 is 10, K2 is 20, which is fine. You can say K1 is 1, K2 is 2, which are also okay. So later on, we also talk about other performance, not just the steady state error. If you, in terms of talk about steady state error, for many parameter selection, they are the same. However, if we talk about some other control performance, maybe it's better to select one parameter versus one set of parameters versus the other set.